Welcome, dynamics students. This mini lecture will include some demo problems on the subject of rigid body planar kinetics. So we will be examining the effect of forces and net moments on the acceleration of a rigid body center of mass when it's moving in planar motion. That means it's moving in one plane, and the vector direction of moments and of all of its rotational velocity and acceleration is normal to the plane. And then we'll be relating the kinematics of the motion to, in a lot of cases, back solve for applied forces that we need to satisfy Newton's second law. So we're going to start with some FBDs in each case that are going to make us kind of tempt us to treat these things like statics problems, but they're not. We'll end up needing the same kind of rigor with our FBDs that we did for statics, but as soon as we have the FBD in place, we're going to be writing expressions for Newton's second law rather than conditions of equilibrium. So that's where we'll deviate, and then we'll use kinematics to relate accelerations to those forces that we've identified from our FBD. So we're going to start with a problem from Hibbler's Dynamics textbook. This is coming from the Hibbler 14th edition, and this is problem 1758. So for this, we've got a plate that's being held up on one side, and we're looking at it the instant in time. I guess it's released from this position at a t equals 0 time. And it's square, and it's 0.5 meters on each side. It's uniform, so it's got a center of mass right in the middle. The hinge point over here is point A, and we'll just call this point O, and O corresponds to the center of mass. And someone wants to know, at the instant at which it's first released, obviously it's going to rotate around, and so we're going to get, it's going to have a different orientation and then reach some equilibrium point, probably kind of upside down, depending on the friction of the hinge and everything else. But at the instant at which it's first released, somebody wants to know, and it has this geometry, what is the angular acceleration? And what are the reaction forces in the X and the Y over at that pin hinge, right at that instant? Theoretically, they would be different as time goes by, and if we drew this in any given geometry, we could solve for that. Certainly we're going to end up solving for an acceleration, so we could take the time derivative of that. If we knew some initial and some final conditions, we could solve for velocity and position. So we could get a position at any time, and then we could go back and see what was going on in terms of use that geometry to recreate the problem. So theoretically, this could be done at any given point in this body's motion. But we're interested in one particular point, which is when the body is basically in this horizontal configuration. And speaking of horizontal, I'm going to go ahead and put a coordinate system here. So I have some sign conventions. So I'm going to be looking at linear accelerations, which are going to be applied to the center of mass, which is at point O, in the I hat and J hat direction. And then because I have I hat and J hat defined that way, positive increase in theta, which means positive angular velocity, and positive angular acceleration is counterclockwise. So chances are this one, we can kind of by observation infer that our alpha is probably going to be negative because it's probably going to be going in the clockwise direction, but that should fall out of our solutions as we go through them. So as promised, we're going to start with an FBD, and I'm going to kind of simplify it and just draw this as a square instead of showing that tab. We'll assume that the tab is precisely in the corner up here. So this is point A, our rotation point, and this is point O. So we're told that the plate is uniform, which means that the weight is acting at the center of mass. So we have a weight force. And then of course we've got I'm going to erase my label here, so I can just replace it with some forces. And we'll assume that we have an upward force at A, and then we'll assume we have positive forces at A in the j hat and I hat direction. Okay, we'll put a little bit of dimensioning here. This will get important. So given that this is a square, that's 0.25, and we have 0.25. And I think we were given a mass for the plate. Yes, we have. It's 24 kilograms. So it's much easier to apply Newton's second law when we have a mass. So from our FBD, we can write Newton's second law expressions. So we can say the net force, the sum of the forces in the x direction, are going to equal the mass of the body times the acceleration of the center of mass in the x direction. So we can say that will equal, wait a minute. So right now we know we have one force. We only have the sum of the forces in the x direction is easy. That's a sub x. So it's going to equal 24 kilograms times whatever the acceleration of the center of mass of that plate is, its x component. Okay, ooh, a sub x. Okay, we can do the same thing with the y. We can take the sum of the forces in the y, and we're going to set those equal to the mass of the plate times the acceleration of the plate's center of mass in the y direction. So if we use our vector conventions, we can express the sum of the forces in the y as just a sub y, the upward force at the hinge minus the weight, is going to be equal to 24 kilograms times a center of mass in the y. So we're racking up quite a few unknowns. We can calculate weight as just 24 kilograms. We can apply gravity times 9.81 meters per second squared if we need to get that. Last but not least, we can look at the sum of the moments. And in this case, we're going to take the sum of the moments about point A. It's a heck of a lot easier for solving the problem. Now this is one of those rare times that we're not going to take it around the center of mass, but we are going to be very careful. And we're going to say that that, in this case, is going to be the rotational acceleration of the rigid body times the moment of inertia, polar moment of inertia taken about point A. And we can take a look at the sum of the moments here and basically solve for that. So if we look at point A as the point about which we're taking the moments, we've basically only got one force that contributes to that, and it's acting at an R of 0.25 meters and then in the downward direction. So that equals, and we're going to end up applying that moment in the clockwise direction, so it'll end up being a negative. So this will be negative 0.25 meters. So that's R cross F, and in this case F is 24 kilograms times gravity. And so this is negative k hat. Planar motion, all of our moments and our rotational accelerations and velocities are in the k hat direction. So negative k hat just means it's going to promote clockwise, rotational acceleration. Now, if we happen to know what the polar moment of inertia of this plate was about point A, we could solve for alpha. So that would be one of the unknowns that we need. And then if we had a way to relate alpha to the acceleration of the center of mass in two different directions, we'd be home free. We could then use the A center of mass and the x and y to back solve for the forces that result in it. So let's take a look at, and we'll just change colors here. Let's take a look at our IZ about point A, and let's start by applying the parallel axis theorem and say, well, I can express this as IZ about the center of mass, the polar moment of inertia about O, the center of mass of the plate, plus the radius, this radius, from A to O. We'll just call it RAO times the mass of the plate. And this is squared. So parallel axis theorem. So we could go to the back of our textbook or go to a handbook and look up the polar moment of inertia of any kind of rectangular thin plate or thin object, and we would find that that ends up being the mass of the object over 12 times basically the two edge dimensions squared. So if this were a rectangle, basically, A by B, and we were looking at the polar moment of inertia about the center of mass in the middle, it would be this. So, okay, in our case, A and B are the same, and they're both equal to, they're both equal to 0.25. So this is really equal to, since we have a mass of 24 kilograms, we have 24 kilograms divided by 12 times 2 times 0.25 meters squared. So that all adds up to, surprisingly, 1 kilogram meters squared. Now that's convenient. So our polar moment of inertia of the plate about point A is equal to 1 kilogram meters squared plus the square of the radius, the distance from A to O, which we can get with Pythagorean theorem. That's just 0.25 meters squared plus 0.25 meters squared, take the square root. But since we're looking for the square of it, that makes it even easier. So we can just basically add 0.25 squared times 2. If we crank through the Pythagorean theorem, we would end up finding that r equals 0.354 meters. So we're going to square that and then multiply by the mass again. So again, as a review of the parallel axis theorem, this term basically accounts for the additional moment of inertia contribution for the center of mass being far away from the point of rotation. It's kind of that distance offset, and this all gives us a value of, which I pre-calculated, 4. Nice round numbers in this case, 4 kilogram meters per second, or excuse me, kilogram meters squared. We're not accelerating yet, no per seconds or per second squared yet. Okay, so we can take that value and this value here, and we can plug it in right there and then do some quick algebra and solve for alpha. So when we do that, we can solve for alpha and get an alpha value of 14.7 radians per second squared. And again, it's going to be in the, we'll put a sign on it here. It didn't change sign because moment of inertia is always it's like positive or 0 for a particle, but it isn't going to have a negative sign. So this was in the negative k hat, meaning it's going clockwise. So alpha stays clockwise, and of course planar motion says it's in the k hat direction. And so we got that by taking our 4 kilogram meters squared and putting it in here, 4 kilogram meters squared, and then dividing both sides by the 4 kilogram meters squared. So canceled kilograms, canceled all these meters, and so we're left with it per second, divide both sides by 4. We'll end up with 14.7. Okay, so now the trick comes is how do we relate the ACM, the acceleration of the center of the mass versus alpha? How are those two related? Well, we have to use the kinematics of motion in this case to find a relationship between those two. So let's budge up and give ourselves a little bit of room here. And let's leave to where we can see a little bit, see our FBD again, because it's also a nice figure. Okay, and we'll switch colors for ease of observation. So now let's switch gears and think kinematics. And of course I'm going to redraw this just to get an idea. So now we're looking at motion of the center of mass. So I'm going to draw myself a little radius here, AO, and I have an alpha. So I can take a look at this right now and say, okay, I have a rotation about alpha, or excuse me, about alpha. Alpha is a rotation. I have a rotation about point A. I know what that is. It's 14.7 radians per second squared. And I have an R. So I can basically look at point O as kind of moving around a fixed pivot. So it's going to end up going on a kind of a circular, it's going to be traveling on a circular path. No kind of about it. It's on a circular path. So I can relate, basically, in this case, it's going clockwise, alpha. So I can look at the vector ACM as simply being tangent to point O at this point. We don't have because we're looking at the instant it's released from rest. Now if we're going to write out our full expression, then let's just do this for practice since we've done this before. Let's take a little walk back in time to kinematics, and of course it's still valid, so really have to go back in time. R from A to O minus omega squared R AO. So this is a rigid body. This is the expression relating the acceleration of any 2 points on any rigid body. This is a rigid body. We've got 2 points on it, so this applies. We know this. What about that term? This would effectively be our normal acceleration if we were traveling on a curved path. So that's our n, and this is our t for our normal tangent curvilinear motion. Okay, because points on a rigid body are traveling that way, no problem. So let's see if we can find something about omega, which is our angular velocity. So we have one more initial condition. The plate is released from rest. Okay? So what that's given us is not only this really nice kind of convenient, one edge is still horizontal, it also means that omega is 0 at that instant. So that whole term goes away. And so all we have to do is cross alpha into RAO and then pick up the x and y components of it, and we'll have this component of ACM is ACMX, which we need up here, and this component of it is ACMY, which we need. So we're going to get the acceleration of the center of mass from the kinematics of motion, which is this expression. Rigid body, I got 2 points on it. I happen to know the acceleration of point A is 0 because it's a fixed pivot. We're rotating about a fixed pivot. So the acceleration of point O, which just so happens to be the center of mass, is equal to alpha cross our radius from that edge to the center of mass. So just some quick trigonometry there. So basically, once we go through the cross product and then we resolve that full ACM, which is AO, into its horizontal and vertical components for x and y directions, we end up with just 0.25 meters ACMX is going to equal, in this case, it'll be a negative, they're both going to be in the negative direction. So this will be negative 0.25 meters alpha I hat, and ACM Y equals negative 0.25 meters alpha J hat. So they're both going down, and they're both just simply equal to 0.25. That was not the radius of what was effectively the circle that O is traveling on, because we're looking at the two different components when it's at kind of an angle of 45 degrees. Now, we haven't moved 45 degrees, but the center of mass is kind of at an angle of 45 degrees to the horizontal. So these two, now we take these two and they go back up to our Newton's second law expressions. I'm going to scribble all over everything I already had. And we can use those to back calculate our AX and AY. So we had our vertical force at that pin support at the instant that we release minus the weight is now equal to just negative 24 kilograms. So we already have the negative sign with the 24, and now we have the magnitude of AY. Whoops, I missed a 5 here, 0.25. Those are both equal. 0.25 meters times alpha, which is 14.7 seconds to the minus 2. And this is all net downward, weights going in the other direction. So, and that was 24 kilograms times G times 9.81 meters per second squared. So if I solve for AY, first I'll do a units check. I have kilogram meters per second squared. I'm going to add that to a kilogram meters per second squared. That's good. Just a very quick and dirty error check. I get 147.2 newtons downward. I should end up getting that for this result on this side. And then if I do the same with A sub x, it's even easier. I have this relationship. There's only the mass, 24 kilograms, and then my ACMX is just 0.25 meters times alpha, second to the minus 2, and that should give me 88.3 newtons. and that's going in the negative x direction because that corresponds to the direction of our acceleration. So a lot of scribbling, but main steps and main points. We start with step 1. Really replicate your schematic, establish your coordinate system. You're going to need it for all of your kinematics, and you're going to need it for your force tally. So both the directions of motion, your alphas, your acceleration of the center of mass, and linear is all going to be referenced to your to whatever coordinate system that you establish. It'll keep you from having sign errors. Then FBD. Figure out what the net force in each orthogonal direction is, and then stop. Don't set the tallies equal to 0. Next, from your FBD, apply Newton's second law. So do the sum of the forces in the x and in the y and set those equal to the total mass times the acceleration of the center of mass in that direction. Then take the sum of the moments and set it equal to the rotational acceleration times the moment of inertia, which will be different depending on what point you're taking it about. Generally speaking, the bomb-proof way of doing this is to always take the moments, sum of the moments about the point corresponding to the center of mass, and then use the moment of inertia about the center of mass. In this case, we were able to use a different point without invalidating our relationship. Then we will typically need to drop to kinematics to get some relationship between all of these terms. So if you look at these blue expressions, you can see we had 1 unknown, 2 unknowns, 3, 4, 5. Whoa, that's a lot of unknowns. And only 3 equations. So we needed 2 more equations somehow to solve for everything we needed. And what we did is we used our single multi-directional kinematics relationship. Remember all of our velocity and acceleration relationship for 2 points on a rigid body. 2 points, of course, always contain 2 equations. So it's this red good old 2 points on a rigid body acceleration expression that gave us our additional 2 equations. So we back inferred force from acceleration in this case, which is definitely something you'd never do in statics. Acceleration is always 0. So I will try to refrain from making too many parallels to statics, but when I see problems and scenarios where it is really easy to make the wrong expression, I'm gonna try to show the difference between those two disciplines. So that is it for this problem. I'm going to close the mini lecture recording with just this one problem, and then I'll have another couple of very similar problems next that have a little bit different scenarios in terms of the nature of the motion, but we'll go through the same steps of coordinate system, FBD, Newton's second law, what kinematics can we apply, how can we work back through the math to solve for what we need.